Okay, so we were almost done talking about limits. Last time we talked about, we never really made a definition of a limit. It's just a little too hard to, it takes a little bit of time. It's hard to wrap your brain around, and this is not really quite what Math 212 is about. But we talked about certain key features that are certainly clearly necessary to have a plausible assertion that a limit exists, and we talked about how to observe that they might fail. So in particular, if you can find different paths along which the function is approaching different values, you have this kind of a situation, right? Clearly this is not a case where we want to say a limit exists. There's clearly some sort of a break of some sort in the values of the function at the point in question, because it depends on how you approach. So that, in a very large number of circumstances, will allow you to conclude that a limit does not exist. Unfortunately, failure to find such a contradiction doesn't prove anything. As I like to say, it might just mean that you're bad at this game of finding such curves, right? Just because you personally can't find a contradiction doesn't mean there isn't one out there somewhere, right? So the looming question, how can you ever show that a limit actually does exist? Well, so we talked about one method last time, and that is to observe that every time a path has, that the path approaches the origin, the polar coordinate r approaches 0, and vice versa. Every time r approaches 0, that path has to be approaching the origin. So these are really synonymous, right? And most valuably, that turns a multivariable limit question into what is kind of, from a certain point of view, a single variable limit question. It does remain that we don't have any control over what theta does, and so there's this worry of if I don't know what's happening to theta, how could I possibly conclude what happens to an expression involving theta? And we observe that, well, yeah, you do get lucky sometimes. So, for example, here, I have no idea. Well, just because r is approaching 0, that doesn't tell me anything about theta. Theta could be going all over the place, wacky, crazy formulas for theta. But no matter what theta is doing here, this expression is bounded. And something that's bounded, when multiplied by something that's approaching 0, doesn't really matter how crazy it is, right? So this limit, in this case, is 0, yeah. That's the idea here, right? So in some cases you can get down to a conclusion like this, but notice the only reason that we get to draw a conclusion is because when we switch into polar coordinates, this happens to be in a form that we can make an actual legitimate argument about, right? So it is not always the case that this will work, right? So there's not a guarantee, right? But sometimes if the stars align just right, this will work very nicely, yeah, right? Okay, so what else can you do? I want to come at this from a weird point of view. I want to seemingly depart to the question of how do you compute limits, and seemingly move on to the question of what can you do with limits. It's going to turn out this is actually a tool for computing limits, after all. So anyway, here we go. Let's define seemingly new idea of what does it mean for a function to be continuous. I know this should be a flashback. This is the next thing that comes up in a single variable calculus class. Right after you define limits and compute limits, then you define continuity. Okay. And we're going to make the same definition here for a function to be continuous at a point A. The value of the function has to exist. The limit has to exist. And those two things have to be equal to each other. It's practically a theft of the definition that we made in the single variable case. Straight out of the single variable case. If these conditions are satisfied, then that means you can conclude that the function's continuous. All right. So here's how we're going to take advantage of this. We're going to turn this into a computational tool. Notice that this is if and only if. That means that the implication arrow goes both ways. That means I can turn this around and point out that if somehow you should happen to know that your function is continuous at the point in question. If you know that, that's a big if. But if you do, that tells you, among other things, a handy-dandy formula for how to compute that limit. Specifically, the way you compute that limit is whatever point you're approaching, you just plug that into the function, and that's the value of the limit. Right? Almost seems too easy. Right. But again, this is the great news that comes out of knowing this huge amount of information. If you know the function's continuous, then yeah, computing limits is easy. Right. Okay. Then the circularity question comes up. If I have to use the limit to prove continuity, how can I use continuity to compute a limit? Right? Circular arguments. Doesn't make any sense, right? That's certainly not a legitimate way to approach things. And here's why that isn't that. We're not going to make this circular argument. We're going to take advantage of work that's already been done. Mathematicians have sat around and looked at the definition of a limit and come up with limit laws and gone to great effort to prove the values of limits in a very broad collection of cases, and have therefore already confirmed for a very large number of cases certain functions that are continuous. So polynomials, always continuous. That's been proved. You don't have to reprove it. It's been proved. We get to take advantage of it. Right? So that's wonderful. So such functions are continuous, and therefore, if you're looking at a polynomial, you want to compute a limit, you take that A, you plug it in there, and there's your formula for the value of that limit. Always works for polynomials because it's been proved that polynomials are continuous. And then on down the list, exponentials, always continuous. Et cetera, et cetera. Now, I am going to put in a little bit of an asterisk in here, and that is where they are defined. Now, good news, polynomials are always defined. Exponentials are always defined. That's not an issue. Log functions, though, are not always defined. So we cannot say logs are always continuous, because they are not always continuous. Sometimes they don't even exist. Certainly not continuous where it doesn't exist. What we are saying here, though, is this refined statement that where they are defined, logs are continuous. Where they are defined, trig functions are continuous. Now, you may object. What about tangent? Tangent does this nightmarish, it's got this dramatic discontinuity in various places, right? How's that continuous? I'm not saying it's continuous at that point, because at that point, tangent is not defined. Right? By the way, don't make sure we're not mistaken on some people think that tangent of pi over 2, for example, is like infinity or something. This is not true. Tangent of pi over 2 is not infinity. It's just not defined. Right? So if you have any questions about that, come to my office hours. I'll be happy to explain in more detail about that. So all of these functions are continuous where they're defined. So if you find yourself looking at one of these functions, just confirm that the function that you're interested in is defined at that point. You can then cite this theorem and say, therefore it's continuous. And then you can say, and because it's continuous, I can compute the limit with the plug-in formula. Okay. Now, here's where the news gets even better. Not only is this long list of functions continuous where they're defined, sums of those functions. So, for example, if you think about it, if you have a polynomial plus an exponential, that function is not a polynomial. And it's also not an exponential, and so it doesn't really fit the above form, right? But so there's value. You get an additional long list of functions by knowing that sums of continuous functions are continuous. Furthermore, products, quotients, compositions are continuous where they are defined. And again, you got to be really careful about this, where they are defined. So, for example, quotients, right? Watch out for the denominator being 0. If the denominator is 0, I don't care what the numerator is. If the denominator is 0, that quotient is not defined. Right? So, super careful with that. Okay. All right, so between the two of these theorems, we have a tremendously long list of, expansive list of functions that are known already to be continuous. So, for example, let's look at this seemingly nightmarish question. right? Oh my gosh, what a horrifying combination of complicated, scary-looking functions. But they're all on the list. These are known continuous functions. And I got a couple of things I need to worry about. Got to worry about the possibility that, what if tangent is not defined? Got to check that, right? Got to take this value of y here. You got to plug that in there and ask, is tangent of pi over 3 defined? Yep, no problem. Right, so no issue after all. You've got to worry about, is this log defined? Be careful. Right? Logs are very often not defined, but you take this x and y, plug it in. Is log of 4 defined? Yeah, sure, no problem. Right. What about the fraction? Right? Is this denominator 0? Nope. Right, so there's only so many ways that this function could fail to be defined. None of them happen. What we have is a quotient of two known continuous functions. This is a known continuous function because it is a sum of two known continuous functions. How do I know these are individually continuous functions? Well, this is a product of known continuous functions. This is a composition of known continuous functions. And so, per the above theorems, this is continuous. Therefore, I can just plug in, take 3, 1, plug into that great big formula. That's your value or your limit. Everybody see the argument there? Yeah.
So for any quotient, is it enough to just show that the denominator doesn't go to 0?
For quotients, that's the problem. Yeah, right. So I mean,
for rational functions, don't you have to show like horizontal and vertical asymptotes? So like, how would you show that? The
question that you're charged with is determining that the function in question is a quotient or combination of sums of products or compositions of these known continuous functions, right? So you don't have to worry about asymptotes and stuff. That's just not your problem, right? The question is the function defined, right? If it is defined, end of story. You get to use the plug-in formula and everything's good. And the only way a quotient could fail to be defined is if the denominator is 0. Right? Now, of course, then you got to look inside, right? I mean, there is the question of is the numerator defined? You got to look at every single part of where could something fail to be defined, right? But as far as a divided by b, the only way that could fail to be defined is if b is 0. Yeah, right. Okay, so now don't get too excited about this formula. It's commonly overinterpreted. A lot of students love to just say, all you need to know is just take this thing and plug it in there, and bam, look, it says so right there. This is how you compute limits. That is wildly, dramatically, catastrophically false, right? If you do that on a test, and if the function in question is not continuous at the point that you're plugging in, right? And then you plug in and you get that it doesn't exist and therefore conclude that the limit does not exist. Okay, that's dramatically wrong. It has no bearing on reality, has nothing to do with the valid analysis of the question, and tragically, since there's nothing correct on the page, that would be worth 0 points. Right? So this is a dangerous tool. This continuity thing. It's a very dangerous tool. It's super useful when it works, when applied correctly, right? But if not applied correctly, it's catastrophic. So it's kind of like a hand grenade in that sense, right? So be careful. Use proper usage of this tool. Okay, moving along. So that ends the discussion of limits. I'm going to move on now to chapter 13. Here it is, week 4 of the class. We're finally going to really start talking about actual derivatives. Asterisk. I know we've already talked about derivatives of parametric curves, but let me just point one thing out. The derivatives of parametric curves, the parametric curve is a function of one variable. Really, you get right down to it, a parametric curve is a kind of a single variable function in the sense that there is a single input variable, t, right? So notice the formula we wrote down for the derivative of a parametric curve is the same old formula, just kind of, applied in different context. So really, honestly, kind of a single variable derivative. So here we are going to do our very first truly multivariable derivatives starting nowish. So before I get into it, I do want to set a little bit of a context. Please don't overinterpret from this very first derivative I'm going to talk about. It's going to be the partial derivative. Some of y'all may have seen partial derivatives before. That's cool. Great. Please don't overinterpret from the fact that this is the first one. A mistaken conception, in my opinion, is that a lot of students believe that this is what a derivative really is, and that there are many things that you can do with it. And it's not technically a false statement, but I think that's a very unfortunate point of view. I would rather say it in a very different way. There are lots of kinds of derivatives. There is no single thing that is the only notion of derivative in a multivariable context. Certainly not a partial derivative. So don't think of the partial derivative as the only derivative. Think of it as, hey, this is the first of many. And there are relationships between the different kinds of derivatives we're going to present. For sure. Lots of relationships, right? But the idea that this is somehow fundamentally the cornerstone, that's what derivatives really are, I think that's a bad choice at best. Anyway, like I say, first of many. This is not in any sense my favorite notion of derivative, by the way, in multivariable calculus. So, in fact, if it was entirely up to me, this would not be the first one I would even present. And it's arguably, relatively unimportant from a sort of foundations point of view. Okay. All right, so when I say there's lots of kinds of derivatives, if they're all different things, why use the same word for these different things? Right? What is it that all these derivatives have in common? And roughly speaking, this is the unifying idea that I think links all kinds of multivariable derivatives that we're going to talk about. All derivatives are relationships between input changes and output changes in their own different ways. Okay, so this is what if you are going to hang your hat on one notion as being what derivatives are about in a multivariable context, please hang your hat on this concept. Derivatives are relationships between input changes and output changes, broadly speaking. And then, there's several different examples. Partial derivatives are one of those many examples. But this is the big idea right here. Everybody see where I'm coming from on that? Now, this is going to play out over the next several weeks, right? But I just want to get us started in the right direction. Okay, so with that context established, we are now going to isolate our attention to a single kind of derivative. We're going to talk about something called a partial derivative. It has a lot of great uses. It's a good thing, right? Overappreciated though it may be. I am going to start with it, but largely because the book does, and I don't want to deviate too far from the book's perspective. And here's why the book starts with partial derivatives. It turns out they're super easy to compute. I circled the wrong thing. They're super easy to compute, and that's nice. That's convenient, right? Partial derivatives are super easy to compute. They're also relatable. They're going to look and feel a lot like single variable derivatives. And if you're already comfortable with single variable derivatives, then starting with something that's familiar to single variable derivatives, it's an easy on-ramp, gives you a feeling of satisfaction, and I see where this is going kind of a thing. So that's a good motivation to want to start with that. Again, I feel it necessary to point out that just because it's easy doesn't mean it's right. Okay, so be aware, again, warning, right? This is just one of many points of view. Please don't sort of go too all in on partial derivatives. Okay, enough of that. So here's how you define a partial derivative. We've got a function of multiple variables, multiple input variables. How do you define derivatives when you have multiple input variables? Well, here's one approach we could take. I know how to define a derivative if you have only one input variable. So let me just kind of cheat in a certain sense. I'm going to say, okay, look, there's a bunch of input variables, but let me just kind of hold the vast majority of them constant. Let me just pretend that I don't actually have a bunch of input variables. Let me momentarily pretend that there's really only one actual variable. These x1 through xn, I'm going to just pretend that most of them are constants. Right? I'm going to just, for the purposes of this calculation, I hereby decree those numbers shall not change. They are now constants for the purpose of this consideration. And if they're constants, they're not really variables. And what I have now is a single variable function. And so with this constraint of holding all the input variables constant, except for one, right? I have a single variable function, and I can just write down the single variable derivative, right? Good old Calc 1 derivative, and that's a thing. It's a kind of a derivative, and it involves this multivariable function f. So this is something that we're going to play with and see if it has any value. Okay, does everybody see where I'm coming from on this? Okay. Now, you should be eyebrow raised a little bit. Why are you just choosing to hold all but one of the input variables constant? Is that legal? Are you allowed to do that? And my answer is, yeah, it's free country. I can do anything I want. Right? Now, when I do whatever I want, it is therefore then, incumbent on me to demonstrate why this is at all relevant to anything, right? I remind you of first day of class, and I talked about, this idea that I had in first grade of let's make multiplication much simpler by just agreeing that 4 times 7 is 47. It's just so easy to compute, right? Problem solved. I just, made math easier, right? No, what I did is I created a construction. Again, free country. There's nothing wrong with me making stuff up, right? But I owe it to my listeners to persuade them that that's in any sense useful. And of course, that concatenation notion of multiplication is not useful. Doesn't relate to anything physical, doesn't relate to anything geometric. I am free to make up nonsense, and in that case, when I was in first grade, I made up some nonsense. So I owe you an explanation of how this is not meaningless nonsense. That's can you do this? That's where that question really leads. I owe you an explanation of why this is useful. And I will give it to you eventually. First, let's revel in the convenience of computing this kind of a derivative. Right now, here's again seemingly scary-looking function. Wow, look at that! It's got cotangent. Oh my gosh, I always hated cotangents. But not even cotangent of a single thing. It's cotangent of a product that involves polynomials and exponentials. What a nightmarish-looking function! And then other factors. Yikes! Right. So, how would I take a partial derivative of this? Well, keep in mind, if you're taking a partial derivative with respect to y, then y is your variable, and everything else in this expression is constant. Yeah. So, yeah, it's a great big nasty function, but for the purposes of a y partial derivative, this is a constant times y squared. Right? So, constant, right? I have a constant times y squared, and the derivative of a constant times y squared is 2y. Times, of course, well, yeah, sure, the constant sticks around. Right? This is basically the derivative of a y squared. And the derivative of a y squared is 2ay. Yeah? Everybody see how that works? It's easy as pie. You can see the appeal. You can see why it's so alluring to think of partial derivatives as being kind of awesome. They are so easy to compute. Everybody happy? Now I remind you, my concatenation formula for multiplication was pretty easy to compute with too. Right? So the fact that it's easy to compute with should not be too... you should still be somewhat concerned, yeah, but what does this have to do with anything? Yes?
Well, it's like the mathematical significance.
Yeah. Well, yeah, that's right. So that's the question that I'm just... So you're right to be worried about that, right? I still need to explain to you why this is at all relevant, and I'm going to get there, which is not quite yet. Here's some other examples, and I just like to get these down just to, because they're easy to do, and I want to remind you and make sure that you're good with the single variable calculus that you should be. Remember, Calc 1 and Calc 2 are in the prerequisite trail of this course. So we will assume in this course that you are proficient with the chain rule, the quotient rule, the product rule, all of that, all the derivative rules, and by the way, pretty soon, all the integral rules, all the antiderivative rules, integration by parts, substitutions, trig substitutions are one that very commonly slips under the radar. Make sure you're good at trig substitutions and these kinds of things, right? It's all unavoidably going to be necessary. We're not quite there yet. Right now we're still doing derivative rules. But so let's attack these. Here I want to take a partial with respect to x of this expression here. And notice I have here a function of x. There's also this y sitting over here. Y is a different variable other than x. And therefore, for the purposes of this x partial, that y is a constant. So while at a glance, this top example looks like a function to the power of a function, and y'all may have flashbacks of logarithmic differentiation. Have y'all seen logarithmic differentiation? It's a clever move. But if you have a function to the power of a function, how do you take that derivative? It's not a power rule. It's not an exponential. It's sort of the worst of both of those. Logarithmic differentiation is a nice trick. If you've forgotten, or if maybe your calculus background maybe didn't include that, I would encourage you to look that up. I'm sure it's all over the internet. But logarithmic differentiation would answer that. Here's the thing. That's not what this is. Right? It looks like a function to the power of a function, but for the purposes of a partial with respect to x, what I'm looking at here is a function to the power of a constant. And this is just chain rule, power rule. Straight up. Right? Function to the power of a constant. Function constant gets kicked out to the front, -1. That's the power rule. Don't forget the chain rule. You have to write down then the derivative of that inside function. It's just basically the power rule, chain rule. So it's a very easy derivative to compute. Everybody on board? Okay. All right. Again, here's another one. Partial with respect to z of, well, I got this big expression. Again, it looks like a function to the power of a function, but it isn't. That's z is the only actual variable. All of this here is a great big constant. So this is just a constant to the power of z. This is just the exponential rule. Right? And so, boom, there's the formula. Now there are some cases where maybe for example the product rule might come up. Here I'm taking a y partial, there's a y, there's a y. So here I really do, kind of unfortunately have a product of two functions. So I do have to use the product rule here. And so you see we get a sum of two terms because of the product rule. First you're taking the derivative on the left side, then the derivative on the right side. Each of which is a partial derivative question, and each of which is an easy partial derivative question. So I'm not saying it'll always be a trivial thing. Sometimes there are multiple steps. But the beautiful thing is when you're taking partial derivatives, you get to look at the expression you're differentiating and just treat large fractions of that expression as constants. It's awesome. Right? It's very, very convenient. I would pose that taking partial derivatives is, in terms of process, in terms of execution, easier than taking single variable derivatives. Because at this point, I get to just pretend stuff is constant. You couldn't do that in Calc 1. Just say, all this stuff here, wow, that looks hard. I'm just going to treat that as a constant. Right? You lose lots of points because you're not allowed to do that. Here, you get to do that for free in certain circumstances. Okay. All right. Okay, so now, the big question. What does this have to do with anything? Why do I care about... I've made up a formula that's highly suspicious of... I'm going to exercise my rights in a free country to just choose to treat certain variables as being constant. Again, highly suspicious that is at all meaningful. So... let's address this question now. Okay, does this geometrically mean anything, or is this just a bunch of, symbolic, useless garbage? Okay. Always a concern when you make a definition maybe what I just wrote down is irrelevant to everything. Okay, so here we go with the interpretation and the observation. By the way, we're going to look at this in the context of graphs first. Now, please recall that I made this observation pretty recently, this week I think it was, that we have to really worry about, am I looking at a graph or am I looking at a level set? Because the calculus of those different constructions are different. What geometrically does a partial derivative look like in the graph context is going to be really different from what it looks like in a level set context, etc. All right, so to be clear, I'm going to start by thinking about in the graph context. Okay, so we're going to suppose we have a function of 2 input variables, all right, 1 output variable, nice easy starting example, and turns out that everything that we have to do in the process of taking, for example, a partial with respect to y, we have an existing geometric interpretation of every step in that process. So, for example, if you're taking the partial with respect to y, the very first thing you do is you fix x. You say, y is my only variable, so I'm going to pretend x is not allowed to change. And now in the graph context, fixing x means you're going to restrict your attention to that plane where you have a constant value of x. And that, of course, takes a cross section of the graph, and that restricts you then to looking at that cross section curve there. So I have an existing geometric interpretation there when I fix x. Yeah? Okay. All right. So next step, when I take the derivative with respect to y of that resulting single variable function, well, the derivative with respect to the input variable, in this case y, of a single variable function, again, we already have an interpretation. The derivative relates to a graph by way of slope of the tangent line. Okay, so putting all of this together, you're looking at a graph. So again, this is important. The surface in question. Going to pen mode. Z equals f of x, y. Right? If you were looking at a graph, very importantly, graph of that function f, then the partial derivative is the slope of that line. So the partial derivative, it's the slope of, there's a lot of words that have to go into this, so bear with me here. It's the slope of the tangent line. Okay, wait a second. Which tangent line? There's lots of tangent lines to this curve, to this surface. There's, which way are we going? There's a specific tangent line here. We're looking at the slope of the tangent line in the y direction. And just for emphasis, reminder, the tangent line to the graph of the function. Right? It is not the slope of the tangent line to a level set of the function. Right? We're not talking about level sets here. We're in the graph context, so we're talking about tangents to the graph. Okay, so incorporating all of the important details of the interpretation, this is what a partial with respect to y looks like. It's a slope of a tangent line to the graph in the y direction. Y direction, because we're taking a partial with respect to y. Everybody on board? Well, by the way, that's pretty geometrically natural. Right? I mean, slope, we've certainly got lots of experience in seeing how slopes are useful things. Right? So this is a particular kind of a slope in the graph context. And furthermore, it's a pretty natural slope to want to talk about. There's a particular cross-section, a particular tangent line, a line that moves in the y direction. It's kind of exactly what you would think it would be. Okay. All right. So by the way, so that is our justification of just making up this definition. I choose to hold all of the input variables constant, except for one. Seemed like an arbitrary and potentially nonsensical choice to make, and I feel like I've now justified it. It is geometrically natural in this way. Everybody on board? Okay. All right. Now here's an exercise for you guys to fill in on your own. What would it look like if you're taking a partial with respect to x? Now keep in mind, if you're taking a partial with respect to x, that means x is your only variable. You're going to treat all of the other input variables other than x as constants. So you're going to be treating y as a constant. There's y. Here's what it looks like when you treat y as a constant. You set y equal to a constant. You're looking at a plane perpendicular to the y-axis, which means you're taking that cross-section to the graph, giving you that curve. You're taking the derivative with respect to x. As you move in the x direction, then you're then looking at the slope of the tangent line to that cross-section curve of the graph. That makes sense to everybody? So I went through that very, very quickly. I want you to think that through slowly and carefully. Persuade yourself that this is what that is. Okay. All right. All right. Totally analogous to this analysis here. Okay. All right. Now, reminder, we're not always looking at graphs. We're often not looking at graphs, right? So I've given you a geometric interpretation of the partial derivative in the graph context, and that's nice. But what if we're not looking at a graph? Now, what does partial derivative look like? How do you think about it? By the way, for those of you who had a high school course in multivariable calculus, very often this is another thing that also gets kind of swept under the rug. They don't cover as much material, and they'll, routinely say, "Well, we'll just talk about partial derivatives in the graph context, and we don't want to talk about these other things." And so this might be a new concept for a lot of you. If you've had a high school multivariable calculus course, and you're thinking, "Well, I didn't see this in my course," okay, that's because your course was very unfortunately incomplete. Okay, this is a really important idea. This is not a who cares idea. This is a really important idea of how does it look in other contexts. So let's suppose, for example, that we have our function f, and remember sometimes we just draw the domain as a separate little world, and we draw the target as a separate little world, and I can conceive of the function like this. It doesn't make for a very good picture. I can't see a nice pretty thing like a surface or a curve or something like that. But this is pretty representative of what's really going on. We've got inputs that are, you can think of as vectors with 3 coordinates. They go into this function, then out comes an output, which is a real number. This is kind of a natural way to draw, to represent what a function is doing. Okay. So in this context, what is a partial derivative? And again, let's start off with partial derivative with respect to y, arbitrarily. Partial with respect to y. Well, that means that of these 3 input variables, x, y, and z, of these 3 input variables, x and z are constant. Right, so from this point, we're going to fix x, we're going to fix z. Those are now not allowed to change. And then we're going to move in the y direction. So from this point, I'm going to start moving that way. Yeah. As you move in that direction, we're going to be keeping track of how f is changing. Oh gosh, let's see, I'll use red, I guess, I don't know. And so as you take off and start moving like that, you're changing the inputs. Of course, you're also going to be changing the outputs. There's going to be a corresponding change in f. So let me highlight this better. So what is the partial derivative here in this in this geometric perspective? The partial derivative says what's the relationship between this input change and this output change understood with these constraints. Now, it's not a slope. And it's also not a familiar, perhaps, way that we've thought about derivatives in the past. But this is what it is in this if you choose to draw your domain over there and your target over here, very natural, right, then this is how you have to interpret partial derivatives in that context. It's a relationship between input changes and output changes, and it's like I say, a pretty natural point of view. Okay, so note how different this is from the whole slope of a tangent line point of view. Okay. All right. Here's a different context. Let's suppose we are looking at level sets, which again, by the way, we were not here. This is not a level set point of view. This is just a different point of view, right? But if you are looking at level sets, what do partial derivatives look like here? Common mistake. Lots of students mistakenly think that, oh, well look, that partial derivative, look, it's a derivative with respect to x. I remember. Oh, Calc 1. Derivative is, that's the slope of that tangent line. And this is absolutely false. That's not at all the slope of that line, because that's not a graph, right? The single variable derivative. Let me preface this comment with, I'm sympathetic to the high school context. They don't want to constantly say slope of the graph, because every picture they ever draw is a graph. And it's like, why would I keep saying of the graph? It's of the graph, of the graph. It's always the graph. Why am I repeating myself? And so very often they'll just say, yeah, it's the slope, right? But in this context, again, the distinction is really important. This is not a graph. That derivative is simply not that slope. All right, so let's come at this from the point of view of input changes and output changes. By the way, remember, level sets represent constant values of the function, so every point on this, oh man, I made it too big. Every point on this curve has the same value of f. Every point on this curve has the same different value of f. Right? So let's think about two different partial derivatives. Let's start with the partial with respect to x. The partial with respect to x says as you move that way, how much is the function changing? What's the output change per unit input change? And my gosh, we just crossed like 4 contour lines, right? Change x by the amount that I've indicated there, and we're just crossing lots and lots of contour lines. There's been a lot of change in f. Per unit change in x. So that means that how to quantify this from the picture is hard to say, right? But in some sense, we feel like this partial derivative is large because the function's change is large per unit distance traveled in the x direction. Whereas on the other hand, what is the partial with respect to y? Oh, I hit my elbow on that. Sorry. Partial of f with respect to y. Let me move now in the y direction, kind of the same amount. I barely crossed 1 contour line. Moving in the y direction, the function hasn't changed anywhere near as much. Moving in the y direction, so the partial with respect to y is relatively small. Right, so, one point of view you could take on this is that in this level set context, partial derivatives are telling you in different directions how close are the contour lines in those directions. These contour lines horizontally are close together. Vertically, these contour lines are not very close together. And now there's kind of a reciprocal relationship. The closer the contour lines, the smaller the distance between contour lines, the more changes there are as you move. So large x partial because the contour lines are close together. Small y partial because in the y direction the contour lines are far apart. Okay, everybody on board? Everybody see how this is very, very different from the graph interpretation? Okay, all right. Okay, so always interpret appropriately in these different contexts. Always different pictures. Okay, let me remind you of some things from single variable calculus. I'll be quick about this, but there's this idea in single variable of the linear approximation. Y'all have memories of linear approximations, and you can write down this formula. And again, y'all have seen this a million times. Let me remind you what makes this an interesting formula. This linear approximation function. This linear approximation function is the unique function, but certain conditions being satisfied for f, is the unique function that has the same value as f at a and the same derivative as f at a. Now, this is a purely algebraic statement here. We're not drawing pictures yet. We'll get to the pictures. Right? But this function is mimicking f. That's the way I like to think about linear approximations. It's mimicking f in both what the value is and how the value is changing. Right? So it's a mimic of f in certain senses. And by the way, you can directly confirm that this is the case. Plug in x equals a into here. If you plug in x equals a, and this whole thing goes away because a minus a is 0, and L of a is equal to f of a, as required. Right? Furthermore, let's take the derivative. Let's take the derivative with respect to x of this whole thing. Let's see here. By the way, don't forget, as x is changing, that's a constant. Very importantly, this is not f of x. This is f of a. A is fixed. So that's a constant. By the way, that is constant. Again, very importantly, this is not f prime of x. That's f prime of a. A is fixed. So that's a constant. So when you take a derivative, really the only non-constant term you have is that there's a constant times x, and therefore L prime of a is equal to f prime of a. That constant, f prime of a. And so this L has the same derivative at a as well. Okay, so y'all have hopefully seen all of that in single variable calculus class. We're going to define very analogously. And then I got ahead of myself. Sorry. So once we have this linear approximation, let's interpret it geometrically. The linear approximation, its graph is the tangent line to the graph of the original function. And again, that's pretty plausible if you think about what's going on here. We've got this, at this point here, we want to find a function that's got the same value and the same slope as the original curve. I appeal to your geometric intuition. That's going to be the tangent. It should be the tangent line. And again, there's regularity conditions that I don't want to get bogged down in, but this is what you would expect. Okay. All right. Okay, so now let's do a multivariable version of this. If you have a function of two input variables, this formula right here, I claim, is what we call the linear approximation, in the sense that this function has the same value as f at the point a comma b, and it has the same derivatives, partial derivatives, as f at the point a comma b. So at the point a comma b, this function here is mimicking the behavior of f as much as possible. It's just copying in every set. Where are you and how fast is it changing? This is copying f the same way. So easy to persuade you. If you're looking at the point a comma b, then that's a and that's b, and all of this becomes 0. All right, and thus L is equal to f. And if you want to take derivatives, let's take the derivative, partial derivative now. Let's take the partial with respect to x. When you're taking a partial with respect to x, don't forget, don't forget, this is a constant. This partial derivative right here is not evaluated at xy. That's at the point a, b, which is fixed. That is a constant. And this, again, evaluated at AB, which is fixed. That is a constant. So the partial with respect to x, that's the only term that isn't constant. Everything else is constant, right? When you're taking an x partial, y is constant. So you take that partial derivative and you get the partial of L with respect to x is equal to partial of f with respect to x, as required, right? Same partials. Now, as an exercise, I want for you all to make an analogous calculation and persuade yourself that the y partial of this function also the same as f. It'll be totally analogous to what we just did there. Very quickly, in the same sense that the graph of the linear approximation is a tangent line in single variable context, it's a tangent plane in this multivariable context. In the sense that, well, look, at this point down here, a comma b, we're looking for a function that's got the same height, right, same value, and whose cross-section has got the same slope as the curve in both the x and the y direction. It's just, in both senses, it's sloping the same way the graph of f is sloping, and so no surprise, it's a tangent plane. So this is kind of the equation of the tangent plane then, in the same sense that the linear approximation gives you an equation for the tangent line. Okay. And then very, very quickly, if you have more than two input variables, what happens? The main thing that happens when you have more than two input variables is we can't draw the picture. Right? We run into our own personal weaknesses. Mathematically, nothing particularly interesting happens. And so along those same lines, and this is another good exercise, this function here, you can totally do this for yourselves, this function here approximates f in value and in all of the partial derivatives at the point A. And it's an easy calculation, just like all the other calculations we just did. So now I don't know what to call the graph of this, but I call it the tangent plane, but it's not just a plane, now it's like n-dimensional, so what is that? Okay, call it whatever you'd like, right? But this is this is the linear approximation. It's kind of a tangent something in a graph picture that I just can't draw. But it's still a perfectly valid linear approximation. Okay. Good place to draw the line. See y'all on Monday. Have a great weekend. A quick reminder, don't forget we have an exam on Wednesday. We are today is the cutoff material for the fair game material. There's a lot more that I want to say about partial derivatives, so partial derivatives will not be fair game for the midterm exam. I'm going to send y'all an email today to document that. That'll be everything before partial derivatives that we've done so far in the course. Okay. See